Okay, so like we were showing in the other examples, the full reaction is when you take these two, they switch partners, they get new partners on the other side. You go and decide if one of them forms a precipitate, and if it does, that reaction does occur. If they are both aqueous on the other side, if you look up the solubility rules, you see aqueous for one and aqueous for the other, then the reaction is no reaction, nothing happens. They're free ions before, they're free ions after, nothing is occurring, nothing's happening, pretty boring. Now, if two of them do decide, though, that they are going to form a precipitate, that's when something happens. You have the precipitate that's forming. You write the net ionic. Okay? We write those free ions with their charges like you saw me do. For some reason, that is something people just forget to do or just neglect to do, and it is marked wrong. In the compound, they are written in their compound with no charges. Unless you want to put them there, you can, but you don't have to. And if spectator ions are eliminated, meaning if they were aqueous before and they're aqueous after, they don't do anything and they are just eliminated, as you saw. So, for instance, again, we have potassium chromate, again, 0 net charge. Barium nitrate, 0 net charge. Sorry, they dissolve in water. Sorry. Now, potentially K could go with NO3, barium could go with chromate like you saw before, so it doesn't really matter which one of those you write first. You could do the potassium nitrate first or the barium chromate first, but we know that Rule 1 and Rule 2 both tell us that this is not going to form a precipitate. But the very last rule tells us that chromates are not soluble. They don't dissolve, they form a precipitate. And so our net ionic here is the barium with a +2, free ion, chromate with a -2, free ion, get together and make two ions that are not free to roam around. They form a precipitate. They are not in solid any longer. And you must put these free ions here, otherwise it is wrong. Potassium hydroxide, K with a +1, hydroxide with a -1. Iron 3 nitrate. Double displacement reaction, K could go with the NO3, but we know again, so it's aqueous. And iron could go with hydroxide. Now remember, iron's a +3, hydroxide's a -1, so don't screw that up. We know from, I think it's the last rule there, that hydroxides tend to form precipitates. Actually, it's not the last rule, it's like 3 or 4th one down. Hydroxides do form precipitates, solids, and so iron hydroxide is going to be a solid. So this would have to be balanced, but the big thing here is the net ionic, and the net ionic is going to be iron with a +3 charge, 3 hydroxides, each with a -1 charge, get together and they do something. They form a precipitate. So that is our net ionic right there. All right, so let you go ahead and do the whole thing together, but what will end up being the precipitate is the lead with a +2, the sulfate with a -2, forming lead sulfate solid. That'll be our net ionic. And cobalt with a +2 and sulfide with a -2 getting together to form cobalt sulfide solid, Rule 6. All right, there's also double displacement when we have an acid and a base. And it's also called neutralization or partner switch. There's a lot of different names for it. It's kind of an overriding name. Specifically, though, an acid base. To know if that's an acid base, first of all, it has to be an acid. And that's going to be H something. Cl, H2SO4, NO3, HBr. And then you're going to have a base, and that's something with an OH. So sodium hydroxide, calcium hydroxide, you get the idea. Strong acids are the only things we look at. Strong electrolytes, they break apart completely. So if I take a strong electrolyte like hydrogen chloride, okay, so hydrochloric acid is a strong acid. Strong electrolyte is going to break apart into a hydrogen +1 and a chloride -1. So those are free to move around and react. Strong bases, and that's all we'll look at, is strong electrolytes completely break apart into a cation of some sort and hydroxide. Now, when these two do a double displacement, it's going to be a salt Now that is salt, but it's some kind of salt, an ionic compound. And water, hydrogen and hydroxide to form water. So what's unique about an acid-base reaction is it's always going to be some sort of salt, which a cation and anion, together with HOH. So let's take a look at a couple of these. Hydrochloric acid, sodium hydroxide, double displacement. The sodium's going to go with the chloride. And we know from Rule 1 and Rule 2, those are going to be aqueous. And then hydrogen gets together with hydroxide. Now, be careful here. That is a liquid. It's not aqueous. So they were aqueous before. They were freely moving around. But they got together and they formed a water molecule. So the net ionic is hydrogen plus hydroxide makes water. That did do something. It formed liquid. Didn't form a precipitate, it formed a liquid. Sulfuric acid, H2SO4, aqueous. Potassium hydroxide. Partner switch, K is going to go with SO4. That's going to be K2SO4. That is going to be aqueous. Plus we're going to have hydrogen go with hydroxide. And that will be liquid. Again, the net ionic is going to be hydrogen plus hydroxide makes water. And please don't bring an H2 over here. It's not H2OH, it's HOH. All right. Net ionic for neutralization is always, it doesn't matter what it is, it's hydrogen plus hydroxide makes liquid water. That's the net ionic for those, always. All right, we're only going to look at one because it has a lot of implications biologically and a lot of different things. But there are, of course, other ones that form gases. But we're going to take a look at something that has an acid. Okay, so I chose hydrochloric. It could be nitric. It could be anything. And then something carbonate. I chose sodium. In your lab, by the way, this will be a solid, but it'll get dumped in. It'll become aqueous pretty quickly. But double displacement, sodium's going to go with chlorine. Please, whatever you do, do not say it's Na2Cl. I will start crying. And then hydrogen goes with carbonate, and hydrogen's a +1, carbonate's a -2, H2CO3. Now, you might be tempted to say that's aqueous, and you should. But what happens, what's interesting about this, is that it immediately breaks down H2CO3 into carbon dioxide gas and water liquid. Okay, now the chemistry there is a lot more complex, but for our purposes, we just are going to talk about liquid water being formed, carbon dioxide gas being formed. And so ultimately, the net ionic for this is hydrogen plus carbonate, making water liquid and CO2 gas. Okay. And again, we would want to balance this by putting a 2 out in front here. But 2 hydrogens and a carbonate ion come together, they form water and carbon dioxide. So that's just the one you're going to be responsible for. You can write it out like this. You can write it like this, however you want to. Just make sure you realize that H2CO3 breaks down into water and CO2. Okay, that's it for that part.